Hi, I'm Sam. Today, I'm proud to present to you our rover team, the RPI Rock Raiders. 1.5 years ago, we created this interdisciplinary team of engineers and scientists to create and design a rover for the University Rover Challenge. We work out of a lab here, in RPI's own Center for Automation Technologies and Systems, where our mechanical, electrical, software, and science sub-teams are working hard to create innovative and unique technologies to integrate into our rover. Here's a brief overview of what we've come up with so far.
The mechanical subsystem consists of the chassis, the drive system, and the arm. The chassis provides a durable enclosure for the electrical subsystem, and the suspension and drive allow for mobility over difficult terrain.
The rover's chassis is constructed primarily from 80-20 aluminum beams that provide a durable and modular frame. The rectangular cross-section provides ample space for electronics and other equipment. The rover's drive system is a 4-wheel drive with independent motors. Suspension is also independently articulated. Turning is achieved through differential torque. The rover is currently undergoing a refit to replace its plastic wheels with superior aluminum wheels of our own design, graciously manufactured by Protocase. These wheels should allow for more effective travel over difficult terrain. For the manipulation challenge, 2 arms are used to accomplish a wide range of tasks. Our modular chassis allows us to quickly swap arms. Fine manipulation of tools and equipment is done with the 6-degree Freedom Canova arm. Its lightweight construction and extremely precise motion is a good fit for small-scale tasks that require highly accurate positioning. These tasks include moving and using tools, as well as pressing buttons such as those that may be found on a keyboard. For heavy-duty tasks, we have constructed a second arm. Powered by linear actuators, this arm's high strength and durability make it a good fit for lifting tasks, such as retrieving large samples. With a maximum capacity of over 20 pounds, the equipment for the science task can also be mounted to the end of this arm.
The brain of the rover is the AIMB274 motherboard, which is powered through a Pico PSU board and a 12-volt regulator. The motherboard interprets data sent through the Ubiquiti M900 to control the rover. Visual data transfer, motor driver communication, and encoder feedback are also facilitated by the rover. An Arduino Uno microcontroller converts analog signals from the sensors to digital signals, which are sent serially to the motherboard.
Communications with the rover occur over 2 Ubiquiti radio transceivers. The module on the chassis has omnidirectional antennae, so we don't have to worry about onboard orientation, while the base station antenna here is powerful enough for several kilometers of range, providing superior penetration through solid objects on the 900 MHz band for when the rover leaves line of sight. Using this bidirectional point-to-point bridge, we can send commands from the base station to the rover, as well as sending back data and video feed. To power all this, a 12-volt lithium-ion battery provides nearly 1,000 watt-hours to allow for extended use of the competition. Of course, safety, both for the hardware and ourselves, was a paramount consideration in the design. So the battery is in series with a 100-amp circuit breaker and an emergency stop relay in case of rapid discharge of the battery. For further magic smoke prevention, each individual component is also placed in series with a smaller circuit breaker according to its nominal rating. So for the science sub-team.
We are using the ROS framework to control the rover and the base station. Our code for graphical user interface, communication, and sensor reading all interface with the modular ROS system. We have also created a simulation to test inverse kinematics of our manipulators. We have used it to verify the functionality of our manipulator design. For the autonomous traversal task, we have created a computer vision neural network to detect tennis balls. It is a ROS-compatible convolutional neural network that can be trained to search for any type of image. It uses the Lasagna library for its neural network base and OpenCV to read images.
The goal of the science team is to search the field for sites that show potential of supporting microbial life. An onboard panoramic camera will be used to search for dendritic channels, which is evidence of water flow. Once a site has been selected, an auger will be used to extract and store soil samples. For sample analysis, our plan is to use a high-resolution camera to search for well-rounded pebbles and well-sorted layers, which is the result of water flow. For the lab analysis, we plan on using a pH probe on the sample. A lower pH suggests the presence of life processes such as respiration.